Data sets in the world are expanding, and the problems that we're trying to answer with those data are increasing in their complexity and their nature, and we need new mathematical and statistical tools to deal with that. So the real challenge is to move from our traditional ways of looking at statistical modelling and analysis of those data and find new ways that are going to deal with these challenges of large data and large problems models. So we're looking here in this program at methods for scalable statistical inference. This is really timely and really exciting to have this meeting now, because these kinds of problems of big data and scalable algorithms and models go across very many areas. They apply in health, they apply in economics, they apply in social science, they apply in environmental studies. And so here we're bringing together not just those problems, but also the ways that we might tackle them. So new algorithms, new models, new computational methods, new ways of making inferences about the data. And so we're seeing these kinds of combinations of people from mathematics, from statistics, from probability, from computer science, coming together to tackle these questions and to build new ways of developing statistical scalable models. So the workshop is looking at new scalable methods in algorithms, models, inferences, computational methods. So in algorithms and computational methods then, we're looking at moving away from the likelihood-based approaches that we've been using traditionally to methods that don't require those likelihoods, because we don't usually have those in really complex problems. So we're looking at, for example, approximate Bayesian computation, scalable Markov chain Monte Carlo methods, looking at Hamiltonian Markov methods. We're looking at variational Bayes and other approaches. We're looking at then sampling approaches like core sets, looking at computational methods like consensus Monte Carlo, so how we use multiple cores and large computational systems. And then we're looking at inferences like exact Bayesian computation. So this is very exciting to work on these kinds of problems, looking at the algorithms, but really trying to understand their performance and the mathematical substance behind them. It goes across many different applications. So some of the applications that were talked about in the workshop were ones about making mobile apps for healthcare, looking at radiological anomalies, so how can you detect, for example, a dirty bomb, looking at transferability of ecological models that are built on systems like, for example, the Great Barrier Reef, and then transferring those models to other unknown reefs, and what can we learn about biodiversity. So there's many real-world applications, but then also these mathematical and statistical models that we can bring to bear on those problems. And how do we scale those so that we can use them for real-world solutions? So this program brings together applications, theory, methods and computation, but it also brings together people not only from different disciplines, but also from different geographic regions with their different questions that they have from those areas. We also then have the opportunity to engage with our broader networks. So we take these insights back and we use them to develop further theory, but also the application and translation. So for example, to policy change, to other researchers in other fields and so on. So what we do here really gets disseminated out through the broader mathematical and statistical communities, but even further then into the broader research applied areas, and then further into policy. This is one of the key equations in Bayesian statistics. So this is Bayes' formula or Bayes' rule. And here we're interested in how we can use this information. So we want to learn about this parameter theta. These are our unknown parameters in a system or a process, given some data. And what we want to use is the information about the likelihood here and prior information we have about those unknown parameters. But this is the problem here, because the likelihood here in large systems really becomes intractable. So there we're looking at approximations for that, or new ways of being able to design algorithms that will allow us to learn about our new parameters, our unknown features of the system here, given the data that we have available to us.